Well, good afternoon, everyone. I'd like to start by saying thank you for making the time commitment to come and be with us. I've been accused many times of being professorial, and my intention is never to be professorial. It is simply to, along the way, I've gained some insights. Sometimes they're interesting insights, and sometimes they show you the way things might actually go. So my intent today is to actually talk about some insights on where things might go relative to agility and automation, and kind of the balanced approach that one needs between performance, price performance, et cetera, and automation and agility. And sometimes these two dimensions are out of whack because people try to emphasize one over the other. When you do that, you get into trouble. So my intent today is really to, in as simple and as straightforward a way, describe at least how I think about these things, and hopefully that'll shed some light for you. If you've already thought about these topics carefully, then what I say will be obvious. So let's begin with the two things I'm going to talk about. I'll mostly be talking about automation and agility, which are on the vertical axis, and performance and price performance, which are on the horizontal axis. So the first thing I'll say is that, at least for our industry, network industry, for a company like Juniper to be competitive, it is exceedingly important to have fast, differentiated innovation. Innovation for its own sake is not effective. It has to be differentiated compared to our competitors. And the way at least I think about our differentiation is that we must be differentiated along these two axes. And in hindsight, I probably should have labeled the vertical axis not automation, but agility, because performance is an attribute of infrastructure. Automation, you can also think of it as an attribute, but what I really mean there is the results of what happens with agility, which is with automation, which is agility. Now, what I've shown here is that generally there is an inverse relationship between the degree of automation and performance. And certainly there is an inverse relationship between agility and performance. So why is that? Well, the reason is that at any given point in technology, if you have a problem to solve that is very specific, I can actually build a specialized hardware for solving that specific problem. And by doing that, I can get extreme performance. But the trouble is that that very specialized hardware may not be useful 6 months from now, because my requirements usually change, because we're all living in a dynamic world, and we have to recognize that. Well, what is agility? So let me define agility first. And this definition of agility has to do with a property of infrastructure. So, a running network is infrastructure. Compute and storage is infrastructure too. So, in fact, when I refer to infrastructure, I refer to compute, storage, and networking sort of as a entire bag. So agility is the following property. Performance, everybody understands, right? Bits per second, packets per second, price performance. If you're talking about compute, it's MIPS per dollar. If you're talking about storage, it's megabytes per dollar, et cetera. But agility is not so obvious. So let me define it for you carefully. Agility is simply the following property. It is the speed with which I can get infrastructure to do something that was unanticipated. So think about that for a second. So I bought a piece of infrastructure, let's say a computer or a machine, and all of a sudden I need to do something that I hadn't thought about before I bought it. Well, if this machine is completely fixed function and the new thing I want it to do, it cannot do, then the agility is 0. Okay? On the other hand, if the new thing that I have to do is possible, but then I have to rearrange the machine and so on and fiddle around with it, well, it may take me more time. On the other hand, if I can sit at a keyboard and maybe type some instructions and all of a sudden configure the machine in a different way, and lo and behold, it does the new thing, well, then that's very agile. So you can see that agility is tied to somehow the degree of programmability of that piece of infrastructure. And in a nutshell, all of this noise around virtualization and actually virtualization, not so much, because virtualization is largely about more efficient utilization of infrastructure. But most of the noise around SDN, NFV, et cetera, has to do with this desire to be more agile. Why do people want to be more agile? Because every business is faced with uncertainty as you look out. You don't know what's going to happen tomorrow, the week after, the month after, the year after. And so you want to be prepared for change. So unfortunately, making things more agile and making things higher performance, at a given point in technology and a given point in time, there is a trade-off to be made. You can't normally get both. So if you want very high performance, well, you have to give up on agility. If you want very high agility, you have to give up on performance and so on. Sometimes, through architectural cleverness or through the advance of technology, you can actually move the trade-off, and you can go from the lower curve to the upper curve. So this thing is actually, this concept is fairly deep. I think that there's some fundamental truth here. So it's worth keeping in mind. Now, let's talk about Juniper. Juniper has actually driven internet performance. It's actually been the leader for driving internet performance. And the proof of this is in the history books now. Before the existence of Juniper, that is before 1998, that is before we actually shipped our first machine, the compound annual growth rate of the performance of the internet was 1.4x per year. This is a doubling every 2 years. No surprise here, because this is exactly what Moore's law says, which is the rate at which computing improves in performance. After Juniper, you can again go back and look. I'm not making this up. It's 1.6x per year. Now, this doesn't sound like a lot, except what you have to remember is that the 1.4 and the 1.6 appear in the exponent. So after 20 years, a 1.4x increase every year is roughly a 840x performance improvement, which is what general purpose CPUs have done. The performance improvement of routers over 20 years has been about 12,000, so 14 times. So you all know about compounding. Compounding is very powerful. Small difference in the exponent makes a big difference. Juniper has been responsible for this. But we have not only innovated in performance and price performance, we've also innovated in automation. So let me give you 3 examples. And these 3 examples have to do with programmability / automation at the system level. System meaning a router or a switch, individual machines. We were the first one to come up with a programmable device interface, a device being, again, a router. We invented the notion of rollback, because oftentimes when you're making complicated changes, you can get it wrong, and it is useful to be able to go back to a previous state. We did that first. We were heavily involved in the definition of netconf and yang, and actually led the industry there to provide an intent-based approach to defining the configuration of machines in a network. So those are 3 examples. So the step after this was good stuff. It was done some time ago. But what we really need to do is network-level automation, right? Now, in actually doing our engineering, our development, we have a thesis. Every company has to have a thesis about okay, what's the overall problem? So this chart tries to define the overall problem, looking through the eyes of our customers. So the cost of owning and operating infrastructure can be is along the vertical axis, and time is along the horizontal axis. Now, infrastructure has both a cost and a benefit. If you are a service provider, the benefit is actually revenue. If you are an enterprise, it's not really revenue, but it's other benefits. Benefits of maybe you're able to do things faster or so on. But the cost is real. Cost is in dollars. And the cost has two components. It has an OpEx component and a CapEx component. The problem, as far as we see it, is that in many instances, especially for service providers, the cost is increasing faster than the revenue. This is very dangerous for any business. So if you're a business where your costs are growing faster than your revenue, you're going to be in trouble sooner or later. But it turns out that when I look at the cost line, the OpEx piece is significantly larger by a factor of 2 to 3, sometimes a factor of 5 compared to CapEx. In other words, even if I drove the CapEx to 0, I will still have a problem. Now, where does the bulk of OpEx come from? Well, a piece of it comes from power consumption, but a good piece of it comes from human resources, that is manpower. So it's clear that what we need to do as an industry, and certainly Juniper is focused on this, is to increase the rate of benefit and decrease the cost so that we have a healthy industry. We all of us dearly want a healthy industry long term. Wall Street is not necessarily concerned about the long term. They're concerned about this quarter. But we have to have a longer term view. Otherwise, we'll all be in trouble because we'll end up with monopolies. Now, as I said, you need to address both the benefit side and the cost side. So let's look at the value chain of what is it that actually affects OpEx, the benefit, and the CapEx. So we know that we want to lower OpEx and CapEx, and we want to increase the benefits. So let's start with performance. Well, if I have something that performs a lot better for the same dollar, it's going to lower CapEx for sure, directly. So that's that arrow. It'll also affect my benefits because I can do more things per unit time. Now, high performance of infrastructure would also affect agility. Why? Because now I'm talking about the performance of my general purpose compute. I can do more things. I can convert things that are done manually to things that are done in an automated way. That makes me more agile, which lowers my OpEx because things are not done in error-prone ways by human beings. They're done by machinery. So that's, this graph is what I call the value chain of how you actually get to lower OpEx, lower CapEx, and greater revenue. So as I said, today my focus is going to be on the automation piece and the agility piece rather than on the performance piece, because in the past we've talked a lot about the performance piece. It does not mean that performance all of a sudden is not important. It is just that where we are as a networking industry, I think that we have done a relatively poor job as an industry on the automation side compared to, for example, the compute industry. And so I think we can take a page from that book and apply some of the lessons, although many of the lessons don't translate directly. And this is, again, a mistake that many of the early SDN proponents made. They said, hey, look over there. This is what happened in the computer industry. Let me directly apply those here. Well, the problem sets in networking are not exactly the same. So it would be a little bit naive to believe that, okay, if I take exactly the same thing, it's going to work beautifully. It might not, and in general, it does not. So another part of our thesis, so the first part of our thesis, going back, is that we need to address both these things. Second part of our thesis is that this is the technological underpinnings, that we are towards the tail end of Moore's law scaling. And this is a pretty scary thing because we have actually, so first let me give you the raw data, and then I'll say what I think about it. So there are three curves here. The vertical axis is a metric of performance for storage, which is in green, for networking, which is in purple, and for compute, which is in blue. And notice this is a log linear curve, so a straight line means that you're improving performance exponentially over time. Well, general purpose computers were invented in 1945. Specifically, the stored program computer was invented in 1945. And I think for a good, all the way to 2004, 2005, we literally had a straight line up and to the right. Through successive technologies, through through reed relay switches, to vacuum tubes, to transistors, to integrated circuits, life was good. Well, the problem is that life is not so good these days. And it's not so good because the basic silicon technology is not scaling. And in fact, we see a point which we're going to come to pretty soon, which is 5 nanometers, which we don't know what to do after that. And the problem is not lithography or anything like that. The problem is transistors stop working like transistors. Or they work as very poor transistors. So this is extraordinarily troublesome, and people have not paid enough attention to this. Please pay attention to this, because this is going to come and bite us big time. And silicon, as you know, is the basis for all information technology. All. Every single thing that I know of is built using silicon. And so software doesn't run on air. Please, for those guys who are waxing eloquent about let's just write more software to fix the problem, it actually runs on something tangible. And at the bottom, it's silicon. Okay? And we have trouble in the silicon house. And trouble is fundamental. People are trying very, very hard to improve the performance, but there is trouble. If you look at networking, networking is going to tail off a little bit later. There are some deep reasons for this. We can get on. I can talk about it if you like, but not now. And finally, storage is going to taper off. And storage tapers off last because storage is employing 3D packaging in the most aggressive manner. So the limits that we are reaching are not just limits of the speed of transistors, the number of transistors I can cram on an integrated circuit. I'm also reaching the limits of how much I/O I can get into and out of a chip. Okay? So both those are problems. And particularly for any-to-any packet switching, that pesky, how many bits per second I can get in and out of a chip is extremely important, because the computation that is being done inside a router compared to the computation that is being done inside a general purpose computer, it's much more I/O heavy. In other words, the number of instructions I run per bit that is coming in is far fewer. Okay? In computing, it's far more. So I/O is less important in computing, although it's becoming more and more important, surprisingly. So what are the implications of that flattening of those, all three of those curves? Well, there are three implications that are exceedingly important. Number one is that this technique of scale out, and I'll define it, will become absolutely pervasive in building all infrastructure. And it's already pervasive inside massively scaled data centers, and it's going to become pervasive inside mid-sized data centers and even small-scale data centers. So what is scale-out? Scale-out is a very special technique where I deploy a number of machines which are identical or near identical. So I pick as few different types of machines, preferably one type, and I just make an array of them, and I connect them with a really high-performance network so that the whole assembly now functions like a single machine. The assumption is that this network that connects these machines is an any-to-any network, typically an IP over Ethernet network. And that if any one of these, and the way I write my applications on top of this infrastructure, this scale-out infrastructure, is that if any one of these machines fails, either because of software or hardware, that the users of this bigger machine don't note the difference, because maybe the network will look, maybe if I'm using a service over the internet, it'll look a little bit slow, and then all of a sudden it'll be fine. This technique is pure genius. It's pure genius because this is what allows me to do DevOps. This is what allows me to write software very quickly, throw it up on the wall, see what sticks. This is what allows me to use my users to debug software. So for example, if I have an array of machines which are all identical, running the same software, imagine that I want to put out a new release of software. How do I do it? Well, let's say I have 10,000 machines. What I'm going to do is I'm going to pick 2 machines at random and put the new version of software on them, and then watch what happens. Right? If the software is brand new, it's probably going to crash, and then I'm going to take a dump of the software and see what happened. And I'll fix it and I'll put it back. Well, next time I run it, maybe the thing runs for a day, and so I get a little bit more confidence, and I say, OK, I'm going to install this on 3 or 4 machines. So notice that the very fact of bringing down a machine and deploying a new piece of software looks to the users as a little failure. That's why this is pure genius. Okay? If I don't do this, and I have this old idea that vendors need to build perfect machines. This is pure fantasy. Nobody knows how to build machines that don't fail. Okay? No one. And if you build your infrastructure on the basis that machines will never fail, well, you are going to live to regret it. And what scale-out does is it acknowledges explicitly that for many, many reasons, things are going to fail. And so let me just write my applications that way, and let me build my infrastructure that way. And so life is good. Every single one of the web scale companies uses this technique. And I've given you a cartoon picture of it, obviously. But after probably a decade to 12 years of operation, scale-out has become very sophisticated. So I think for people who are not familiar with this, please get familiar with it. I'm sure most of you are. But this is here to stay. And the point I'm trying to make here is that when the individual elements, when technology is telling us that the individual element, performance per element, is flattening out, only 2 things can happen. One thing that can happen is that the world all of a sudden says, oh, I don't need any more storage, I don't need any compute performance, and I don't need any more network performance. Well, there's a fat chance that that'll happen. Right? We all need more because it's useful stuff. So what's going to happen is people are going to build bigger and bigger assemblies of these things. So computing is going to get scaled out. Storage is being scaled out. Networks were kind of sort of scaled out already in a more sophisticated way because networks are distributed. But the next step that's going to happen is that maybe things like core routers will scale out, maybe edge routers will scale out. That's coming. Now, is scale out the only thing that we can do? No, there's one other thing we can do. What we can do is, today, by and large, web scale companies have very large scale data centers. Each one has maybe 24 data centers around the world. The problem is that I am limited by power, the amount of megawatts I can get into a data center in the number of machines I can put. So let me do the math for you. The largest data centers have somewhere between 150 and 180 megawatts. You spend about somewhere between 400 and 500 watts per machine. You can do the math. You can't cram more than that. So what do? Well, you can build more of them, more distributed. But there's something more interesting that might happen. And that something more interesting that might happen is the following. Human beings are always impatient. And once we get used to a particular level of performance and interactivity in our devices, we want more. Do me the following favor. Next time you're in an airport or somewhere in a social setting, look at the number of people who are doing this on their phone. 90% of the people are doing that. And typically what they're doing is, waiting for this wheel going around and around and around. And it's frustrating and it wastes time. People like interactivity. So, if I have a glass of water on a table and I try to look at it and I try to pick it up to drink it, there's no wheel that goes around and round and round, okay? It appears to me to be instantaneous. So at the end of the day, human beings want to interact with the world in the same way that they interact with the physical world. They want to interact with the virtual world in exactly the same terms. And the magic number for that degree of interactivity is somewhere around 3 milliseconds. So if I can make things happen, if I do something and that some action happens within 3 milliseconds, it will look to me to be instantaneous. And there's some biological reasons for this, but you can read up on that. So it turns out that it would be hugely beneficial that in addition to these large-scale data centers, that we put low-latency data centers fairly close to end users, close enough that I can satisfy the 3 millisecond requirement, including the speed of light delay from the end user to this low-latency data center and back. For example, virtual reality. It is unlikely that we're going to be strapping 5 pounds of NVIDIA gear to our back and with this thing around us in order to benefit from VR. Much more likely it's the case that, and not to mention the power pack that comes with it, the battery pack. Much more likely is the case that there's no reason to carry that thing around, because even if it is 20 miles away, or 20 kilometers away, it's about 360 microseconds away, which is fine, right? The rest of the time I can use for computing. So these low latency data centers will become, I think, pervasive. And this hasn't yet happened, so it'll be a new market. There's one other thing we can do. And this is, I'm making a prediction, and predictions are always fraught with danger. But given this flattening, I think what will happen is that people are going to become much more inventive about how efficiently they use hardware for particular important problems. So what we're going to do is we're going to look at domain by domain. Or what's a domain? Graphics is a domain. So nobody uses general purpose computers to draw graphics, although you could do that, but it's too expensive. But people use very specialized SIMD machines to do graphics. Why? Because they're 20 times better price performance. Similarly, for deep learning, people are now building specialized engines. Juniper itself is a great example. Early on, the first company who actually did a domain-specialized piece of technology for networking, for packet switching, for packet processing. What I'm predicting is that given this flattening, a lot more of that is going to happen. But there's a nuance. Given the importance of agility, even though something is domain specialized, you can still have it be programmable. This is the difference. So I think what is going to happen, my prediction is that that's where the world is going to go. We're going to invent new architectures which are programmable, but which don't give up on performance because they specialize to particular domains that are important. Now, automation. Well, the gold standard here was set by the hyperscale companies. And what they did was they applied computation to manage compute and storage infrastructure. So a little bit recursive, but still comprehensible. So the general picture is that you have this any-to-any network, large number of scale-out servers and storage, and then you have some orchestration software which also runs on general-purpose computers. And this orchestration system manages the resources, makes sure that they're assigned efficiently, make sure that failures are dealt with, and the total number of people that are needed to actually run this, not the programmers, but the operators, is far fewer than you would need if you were doing things manually. Now, the ultimate goal of this is full autonomic operation, where you set up a bunch of policies and rules, and the system actually, the orchestration system learns as it goes, and it becomes more and more efficient over time. This is coming for sure, okay? Now, the network is nowhere near this sophistication, but we need to get there. The networking industry is behind computing in this respect. But the problem is not identical. And there are some real difficulties. So let me just call out the difficulties. First, the scale is huge. We're talking about potentially worldwide scale. And when you have large scale, the only trick that we actually know about is to use hierarchy to manage the number of resources. Second problem we have, which we don't have in computing, is distance. Distance is actually bad news here. It means longer latencies. It means constraints on what computation can be centralized because of speed of light. And finally, distance also means that a lot more bad things can happen. So if I have a data center that I control and I have concrete walls and so on, and all the equipment is inside, it's safe, well, the network, the fibers are running out somewhere. Rats can chew them. There can be a lightning strike somewhere. Things go wrong, and they do. And so failures there are many more diverse causes of failure, and you need to be able to handle them. Finally, if I'm a web-scale company, I can make a fiat that all my infrastructure is the same. When I'm a service provider, typically, I would like heterogeneity to get better prices. And heterogeneity, unfortunately, means added complexity, because every vendor does things a little bit differently. And here, the networking industry has to do better. There has to be much better cooperation so that and NetConf, by the way, was an attempt at doing that. OK. I'm going to speed up a little bit. So some elements of network automation. The operational configuration of networks has to be intent-based. It shouldn't be imperative. It should be declarative. Imperative just means that I'm writing a program that says exactly what to do. Declarative simply means I want to say what I would like to have happen, and I have a compiler that takes what I would like to have happen and make it happen. And that's automation. Service instantiation should follow the same paradigm. Network optimization is clearly something that can happen in a centralized way. Why? Because the time scales of the computation are long enough that the speed of light, the time taken by speed of light, is small compared to those time scales, right? And in fact, in general, anything where the time scales of the speed of light are small compared to that computation can be centralized. Telemetry from individual machines needs to be based on push semantics rather than the old semantics of polling, because that does not scale. And then we need, as an industry, as I said, de facto standards for at least the following 4 things: configuration, for example, OpenConfig, telemetry, service definition, and then path optimization in the network. And finally, we need hierarchical representation of the network resources itself to handle the problem of scale and distance combined, which are very difficult problems compared to centralized computing. So what has Juniper done in this area? Well, let me give you some proof points. OpenContrail, it's the most scalable controller on the market. It is gaining rapid adoption, and it was, I think at the last OpenStack Summit, voted the #1 controller. NorthStar is the most sophisticated path optimization software for the wide area network. And it also does multi-vendor support, not just Juniper equipment. OpenConfig is a standards-based config framework, and we are participating in that. And then there is an Open Collector, which is standards-based telemetry. We are working on that as well. Let's see, what else? So summary. Juniper has led and will continue to lead in performance and price performance. Juniper is investing heavily in leading in automation and agility. And these are the 2 techniques, these 2 dimensions that we're going to use to stay differentiated. Thank you very much.